Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories.
The quiet genius who won the Nobel twice, the untold story of John Bardeen. There's a guy out there won the Nobel Prize, twice, both in physics. And yet, most people have no idea who he is. Every time you unlock your phone, scroll, tap, watch, you're using something he made possible. Funny thing is, he's not a household name. No spotlight. No drama, just quiet work that changed everything. The kind of person who proves still waters run deep. He didn't chase fame. He built the future. Calm, unassuming, almost like the guy next door. But don't let that fool you. Without him, your digital world would look very different. His name? John Bardeen. He wasn't the talkative type as a kid, but his mind moved fast. May 23, 1908. Born in Madison, Wisconsin. A college town, ideas in the air. He grew up right in the middle of it. His father, Charles Bardeen, was the founding dean of a medical school. An anatomist, spent his days mapping the human body. Dinner conversations, not gossip, science. His mother, Althea, had a background in design, calm, thoughtful, steady. The house wasn't loud, but expectations were. 5 kids. He was one of them, quiet from the start, more observer than performer. 1914, he's 6. Starts elementary school. Teachers notice something quickly. He doesn't raise his hand much, but when he does, he's right. While others memorize answers, he's asking where the rules come from. That habit sticks for life. By 1917, he's in a university high school program. Classes get harder for him? Still slow. He starts jumping ahead, taking advanced courses early. So the school does something unusual. They hold him back. On purpose. Not because he's struggling, because he's too far ahead. That almost never happens. Around 1920, his mother passes away. He's about 12. Too young to process it out loud. So he doesn't. He goes quiet. And stays that way. More focused, more inward, emotions dialed down, thinking dialed up. As the saying goes, actions speak louder than words. He just chose thinking over both. 1921. Madison Central High School. Now the material is closer to college level. Math. Physics, especially electricity and magnetism. Invisible forces, clear rules. Exactly his kind of world. Teachers all say the same thing, quiet, but brilliant. Doesn't show off, but almost never wrong. He's not the social type. Doesn't chase attention, stays on the edge of the room, watching. But when it comes to exams, he's always ahead. 1923. He's 15. Graduates high school. 2 years early. Could have been earlier, actually, if the system hadn't slowed him down. That detail matters. He was moving faster than the track allowed and still didn't rush. No celebration. No speeches, barely a trace left behind. Just a quiet exit. A kid who didn't say much, already miles ahead. Empty vessels make the most noise. He was the opposite. Fall, 1923. He's 15. And already in college. University of Wisconsin. He picks electrical engineering. Not philosophy, not pure physics, something practical, something that gets you a job. A safe bet, clear path, good future. And he's good at it. Math. Solid. Physics? Comes naturally. Engineering courses? No problem. But here's the twist, he starts adding extra classes. Not required, not for credit. Math, physics. Out of curiosity. On one side he's learning how to use electricity. On the other, he's asking what electricity really is. 2 tracks, same person. 1928. He's 20. Bachelor's degree done. He keeps going. 1929. Master's in electrical engineering. Right on time. And right into chaos. That same year, the economy collapses, the Great Depression begins. Jobs disappear overnight. But he's in a different position. He has skills, or real, usable skills. So the choice is obvious, go into industry. Around that time, he joins Westinghouse Electric. Big company, part of the telecom ecosystem around AT&T. What does that mean? Stable paycheck. Cutting edge tech. A dream job for most engineers. And at first, it works. He does well, works hard, solves problems. But then something shifts. It's not that the job is bad, it's that the questions are too shallow. He can fix things, but he's not excited by them. He keeps coming back to one thought. Not how does this work? But why does it work at all? That's a different mindset. Less engineer, more scientist. 1930. He leaves. Not quitting the field, just moving sideways. He joins Gulf Research Laboratories. Now it's geophysics. Measuring gravity, studying magnetic fields. Used for oil exploration. Sounds advanced, and it is. But the same feeling creeps in. He's solving problems, not understanding them. From 1930 to 1933, 3 quiet years. And one growing realization. If he stays on this path, he'll be successful. Just not satisfied. He doesn't want to just use the world. He wants to explain it. Now here's the catch. This is the Great Depression. People are desperate for work. And he already has it. A good one. Walking away, that's not logical. No guarantees. No safety net. Starting over. But as they say, fortune favors the bold. 1933. He makes the call. Quits his job. Applies to Princeton. PhD, theoretical physics. That's not a small shift. That's a full turn. From practical to fundamental. From certainty to uncertainty. Most people wouldn't risk it, especially then. But he does. Because he cares more about the question than the reward of the answer. He gives up stability. A clear career path. In exchange for one thing, a chance to understand deeper laws. At the time, it looks like a gamble. Later, it reshapes the entire electronic age. 1933. He's 29. He walks away from a steady research job in Pittsburgh and applies to grad school. Not school. Princeton. One shot. If it doesn't work out, he goes back to industry. No backup plan. That's the moment, all in. And it pays off. He gets in. He enters mathematical physics. That's a big shift. He's no longer building systems, he's trying to understand the rules behind them. Not devices, electrons, how they move, why they behave the way they do. His advisor, Eugene Wigner. One of the best in the field, future Nobel laureate. Wigner works on quantum mechanics and the theory of solids. For him, this is new territory. He later admits when he first arrived he didn't even know what solid-state physics really was. But he catches up. Fast. Quantum mechanics, statistical physics, electron behavior in materials. Now the difficulty jumps. This isn't how do we build it. This is why does it exist like this. From 1933 to 1935, he's deep in coursework and starting research. Focus, electrons in metals. More specifically, surfaces. One key question, how much energy does it take for an electron to escape a metal? That's the work function. Sounds niche. It's not. It sits right at the heart of future electronic devices. Back then, this field is barely formed. No clear roadmap. No finished framework. He's learning it while helping build it. Learning by doing takes on a whole new meaning. By 1935, his results are coming together. He's blending quantum theory with real materials. Not pure math, not pure engineering. Something in between. A new way of thinking. 1936. PhD completed. Mathematical physics. His thesis, The Quantum Theory of the Work Function in Metals. That's the turning point. He's no longer an engineer with theory on the side. He's inside theoretical physics now. And more importantly, he's found his lane. While others chase nuclear physics or particle theory, he looks at materials. At electrons inside them. Invisible behavior inside everyday stuff. Doesn't sound flashy. But here's the thing, don't judge a book by its cover. That path leads straight to the transistor, and everything that comes after. His time at Princeton, just a couple of years. But he later says it mattered more than anything else. Because that's where he stepped onto the front line of science. And started shaping a field that didn't fully exist yet. 1938. He's 30. Leaves Harvard, takes a teaching job at the University of Minnesota. Finally, some stability. A normal academic life. But not for long. September 1, 1939. War breaks out in Europe. At first, the US stays out, but science doesn't. Research starts shifting, quietly, toward war. Then December 7, 1941. Pearl Harbor. Everything changes overnight. The US is in, and so are the scientists. He leaves the university, joins the Naval Ordnance Laboratory near Washington, D.C. Mission: keep ships from blowing up. The problem sounds technical, but it's deadly simple. Enemy mines don't need to touch a ship, they can feel it. Magnetic mines. Steel ships carry magnetic fields, like moving beacons in the ocean. Easy targets. His job: make them disappear. Not literally, magnetically. The technique is called degaussing. Run currents through the ship, cancel out its magnetic signature. Sounds elegant. In reality, a nightmare. Every ship is different, every environment changes things. Saltwater, temperature, direction of travel. All of it matters. From 1942 to 1945, that's his world. Measure, calculate, model, test. Over and over again. His physics background becomes crucial. Because this isn't just engineering, it's electrons, materials, fields interacting in messy, real conditions. No clean equations. No perfect lab setups. And no publications. Everything is classified. No awards. No recognition. Just results that matter immediately. In academia, a mistake means a rejected paper. Here, it means a destroyed ship. Pressure makes diamonds or breaks things. He adapts. Later, he says this period changed him. He learned to respect real-world problems. To see how materials actually behave, not just how theory says they should. That insight will matter a lot. He never joins the atomic bomb project and never goes to Los Alamos. But his work still serves the war. Not by creating explosions, but by preventing them. 1945. War ends. Scientists head back to their fields. He does too. But he doesn't come back the same. He leaves with two things. First, a deep understanding of complex, messy systems. Second, a growing focus on how electrons behave inside materials. Put those together, and the next chapter is already waiting. Bigger stage, bigger impact. Sometimes, what you learn in the storm is what carries you in the calm. October 1945. War just ended. He leaves military research and joins Bell Labs. At the time, it's one of the most powerful industrial research centers in the world, backed by the telephone system. The goal is simple: better communication, lower cost to higher efficiency. He joins a small team. William Shockley leads it, Walter Brattain handles experiments, John Bardeen handles theory. Clean division of roles. On paper, perfect. In reality, problem starts immediately. The mission is big: control electrons. Back then, electronics run on vacuum tubes. Big, hot, unreliable, short lifespan. If you replace them, you change everything. Shockley proposes a new idea: use semiconductors to control current. No vacuum. No tubes. Sounds elegant. But it doesn't work. Not yet. By 1946, they're stuck. Electron behavior is messy, theory doesn't explain it, experiments don't repeat cleanly. Frustration builds. Shockley pushes harder, more pressure, more control. But progress stays slow. Then Bardeen notices something. The problem might not be inside the material, but on the surface. That shift matters. He proposes surface states, air controlling everything. That changes the direction. Brattain adjusts the experiments, new setups, new contexts, and new trials. Test, fail, adjust, repeat. The pace picks up. Late 1947, signals start behaving differently. Not stable yet, but promising. December 16. Brattain runs a key test using a gold point contact on germanium. Signal amplification appears. But it still needs confirmation. December 23, 1947. A simple lab. No ceremony. No press. No noise. Just an experiment. A piece of germanium .2 thin metal contacts. A circuit. Brattain runs the setup. Bardeen analyzes the behavior. Input a signal, check the output. If output is stronger, it works. Current flows in as signal changes, output increases. Stable or repeatable. That's the key. In science, one success means nothing, a repeatable success means everything. They test again, same result. Amplification confirmed. For the first time, a solid material device amplifies a signal. No vacuum tube. No heating filament. No fragile glass. Just a solid crystal doing the job. A new device is born. Later, it gets a name: the transistor. At that moment, no one calls it a revolution. No one says this changes everything. They just record the data, write the report, move forward. In June 1948, Bell Labs announces it publicly, patent follows. Now the world knows. But even then, the scale isn't clear. A smaller device, longer life, lower power. That's what they see. What it really means: smaller machines, faster computing, more complex systems. Decades later, computers. Integrated circuits. Smartphones. All built on that idea. But on December 23, 1947, none of that exists yet. No one is talking about revolutions. No one is predicting the future. They're just confirming one thing: electrons can be controlled in a stable, repeatable way. That's it. Everything that comes after? Someone else builds it step by step. After December 1947, things don't calm down. They get complicated. A familiar pattern in science kicks in credit. The transistor wasn't a solo act. John Bardeen, the theory. Walter Brattain, the experiments. William Shockley, the leader. Take one out, the story falls apart. But success brings a new question: who matters most? Here's where it gets tense. When the breakthrough happened, Shockley wasn't in the room. That detail lingers. Because the result is real and he's in charge, but not hands-on at the key moment. Early 1948. Reports are being written, papers drafted, names ordered. And suddenly, that order matters. Shockley makes a move. He pushes a new idea, the junction transistor. More complete, more scalable, and crucially theory-driven. He knows the game. If the story ends with the point contact version, credit gets split. If he defines the next step, he regains control. So he starts working more independently, less collaboration, more distance. The atmosphere shifts. Fewer conversations, less trust. Bardeen's personality shows here. He doesn't argue. Doesn't go public. Doesn't fight for the spotlight. But silence doesn't mean peace. It means pressure building underneath. June 1948. Bell Labs goes public. Press releases, papers, patents. The world starts paying attention. Inside, things are already strained. Shockley becomes more controlling. Information gets tighter, communication gets filtered. At one point, he even monitors team members. That's not normal for a research lab. But it happens. Brattain stays focused on experiments, keeps his head down, avoids conflict. Bardeen chooses a different path. He leaves. 1951. Less than 4 years after the invention. Not a transfer, not a pause. A clean break. No public statements. No accusations. But the message is clear: this collaboration is over. A team that changed the world can stay together. It happens more than people think. Shared goals disappear, personal ones take over. And cracks widen. He doesn't argue his case. Doesn't chase credit. He just walks away. Back to academia, back to quiet work. It looks like a step back. It isn't. It's a reset. 1956. The Nobel Prize in Physics is announced. All three names are there: Bardeen, Brattain, Shockley. History finds its balance eventually. But the road there, not balanced at all. From the outside, it's a clean story. A brilliant invention. From the inside, it's human. Competition, ego, control. Scientists aren't immune to any of it. If anything, it can run deeper. Because they're not just chasing positions, they're chasing a place in history. The transistor reshaped the world. And the conflict around it reshaped the people who built it. As the saying goes, success has many fathers. But not all of them get along. 1951. He walks away from industry. Leaves one of the most powerful labs in the world and goes back to campus. University of Illinois, Urbana-Champaign, professor. On paper, it looks like a step down. No big lab. No direct line to industry. No spotlight. But the environment changes. No management pressure. No internal battles, just questions. And that's all he ever wanted. So he picks one, an old one. Superconductivity. Discovered in 1911. Certain materials, at low temperatures, lose all electrical resistance. Not less. 0. For decades, no one can fully explain it. Plenty of experiments, incomplete theory. A mystery that just won't go away. Early 1950s, he dives in, but he doesn't follow the usual path. Most people think in terms of single electrons. He doesn't. He starts thinking collectively. What if electrons don't act alone? 1955. He reaches a strange idea. Electrons might actually attract each other. Sounds wrong. They're both negatively charged, so they should repel. But inside a crystal lattice, things get weird. Vibrations in the lattice phonons can create an indirect pull. Subtle, but real. 1956. His student, Leon Cooper, takes it further. Shows that two electrons can form a bound pair, now known as a Cooper pair. That's the breakthrough. Electrons don't have to move solo, they can pair up. Then comes another step. Early 1957. Another student, John Robert Schrieffer, builds the bigger picture. A wave function for the entire system. Not just two particles, millions, acting as one. Now it clicks. 3 people. 1 framework. 1957. They publish what we now call BCS theory. Simple idea at the core. Electrons pair up, move together through the lattice, and avoid scattering. No scattering means no energy loss. No energy loss means zero resistance. For the first time, superconductivity isn't just observed. It's explained, calculated, predicted, testable. After nearly 50 years, the mystery is solved. From 1911 to 1957, half a century of questions. And the answer comes not from a giant lab, but from a quiet university office. No massive machines. No industrial pressure. Just theory, done right. Slow and steady wins the race. This time, it really does. And the impact? Huge. Not just for technology, but for physics itself. Solid-state physics grows up. From trial and error into a fully developed theory. BCS becomes the foundation. Everything after builds on it. 1972. The Nobel Prize in Physics is announced. 3 names again. Bardeen, Cooper, Schrieffer. For explaining superconductivity. He's 64. And this is his second Nobel Prize. But here's what makes it remarkable. First time, he helped invent a device that changed the world. Second time, he explained a fundamental phenomenon that puzzled scientists for decades. 2 completely different arenas, both at the highest level. That almost never happens. Lightning doesn't strike twice, except, somehow, it did. 2 moments. 10 years apart, both changed everything. First, 1947. Bell Labs. One problem: how do you amplify a signal? Before that, it's vacuum tubes. Big, hot, fragile. They work, but they hold everything back. Then comes the transistor. Small, cool, reliable. 3 changes: size, power, durability. That's all it takes to flip the future. 1950s transistors start replacing tubes. Radios shrink, they become portable. 1960s integrated circuits arrive. Multiple transistors, packed into a single chip. Now things scale. 1971, the first microprocessor. Computers begin moving out of labs and toward people. 1980s, personal computers spread. Offices go digital. 1990s, the internet connects everything. 2000s, mobile devices take off. 2010s, smartphones everywhere. Look at your hand. Inside that device, billions of transistors. Switching at incredible speed. Every tap, every swipe, every video. Generated, compressed, transmitted, decoded. Step by step, it all runs on transistors. They're invisible. But they're everywhere. No transistor, no modern world. That's the first story. Second, 1957. Different place, University of Illinois. Different question. Why does resistance vanish? Superconductivity had been known since 1911, but no one could fully explain it. Without theory, you can't control it. Then comes BCS. A clear idea. Electrons don't always travel alone. They pair up, Cooper pairs. Move together through a lattice. No scattering. No energy loss. Resistance drops to zero. Now it's not just a phenomenon. It's something you can design. And once you can design it, applications follow. Medicine. MRI machines, they rely on powerful magnetic fields. Those fields come from superconducting coils. No resistance means no heat. No heat means stable operation. Particle physics. Accelerators like those at CERN. They use superconducting magnets to steer particles. Without them, energy loss kills the experiment. Then comes the next frontier. Quantum computing. Superconducting circuits become one of the leading approaches. Qubits built on delicate, low-temperature systems. Zero resistance isn't optional, it's essential. The future is still unfolding, but the path is set. From everyday electronics to the edge of physics, these two breakthroughs cover both ends. One reshapes the tools we use, the other reshapes the laws we understand. Different directions, same route. Electrons. At room temperature, technology. At low temperature, fundamental physics. Two worlds. One person. Quiet, unassuming. But as the saying goes, big things come in small packages. Twice, in completely different ways, he changed the world. And the ripple effect? Still spreading. Here's a small story, but it says a lot. December 10, 1956. Stockholm. He's there to receive the Nobel Prize. Big moment, global spotlight. But he shows up with just one of his kids. Not the whole family. Why? Simple. He didn't think it was necessary. To him, it's a formal event, nothing more. But someone notices. The King of Sweden, Gustav VI Adolf. During a conversation, he makes a remark. Next time, you should bring all your children. Half joke, half suggestion. Most people would smile, nod, and forget it. He doesn't. He doesn't respond. Doesn't explain. He just remembers. Fast forward 16 years. 1972. Same date, same city. Another Nobel Prize. This time, for superconductivity. And this time, he brings everyone. All three of his children. No announcement. No explanation. Just quietly doing what was once suggested. That's the kind of person he is. He doesn't talk much, but he listens. Doesn't make a show of things, but he follows through. Actions speak louder than words. And that's not just a saying here, it's a pattern. Outside of Nobel Prizes, his life feels ordinary. No dramatic lifestyle. No larger-than-life persona. He lives in a regular neighborhood. Fixes things around the house, chats with neighbors. Most people around him have no idea who he really is. Let alone that he's won 2 Nobel Prizes. He rarely talks about his work. If you ask, he'll answer. But he won't go on. No exaggeration. No storytelling. His interests? Simple. Family gatherings, barbecues, spending time with his kids. He married Jane Maxwell in 1938. Long, stable marriage. No public drama. 3 children raised in a calm environment. One of them goes into physics too. Not unusual in a scientific family. But he never pushes, never maps out a path. He influences, he doesn't impose. If you had to sum it up, his life is ordinary. Almost too ordinary for what he achieved. Most people would tell that story for the rest of their lives. He barely tells it at all. Others lean into titles. He seems to step away from them. But facts don't disappear. 2 Nobel Prizes in physics. Whether he talks about them or not, they're still there. As the saying goes, the empty wagon makes the most noise. He was the opposite.
The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.